The commercialization of computers changed the world of electronics.
I'd also like to have your Caesar salad.
If you wish to send a fax, transmit now.
They drive the information and communication era of today. Inside these machines, we find the integrated circuits which make commercial computers possible. Their evolution from vacuum tubes to transistors to the integration of components has led to the integrated circuits of today's computers and technological centers like Silicon Valley. It all begins with the growth of pure semiconductor crystals, usually made of silicon, an element found in the Earth's crust. Lightly doped silicon crystals are sliced into wafers, which are cleaned and polished on one side. On this polished silicon surface, many integrated circuits or chips are then fabricated. Each one of these chips is a complete circuit, consisting of many thousands of transistors and other electrical components. Each transistor acts like an on-off switch. With this transistor, positive charge to the gate attracts nearby electrons. An electron channel connects the source and drain, which allows current to flow, turning the transistor on. When the gate charge is removed, the transistor is off. This switching creates information as electrical pulses, which are read in the binary language of computers as zeros and ones. There are several major types of transistors. Some of these transistors are grouped to create tiny circuits called logic gates. These gates follow standard rules, known as truth tables, to perform specific functions. The inverter or NOT gate, for example, automatically changes the input to its opposite. These simple logic gates are the building blocks used to design integrated circuits. By properly combining simple logic gates, a designer can create complex functions to implement a vast array of useful operations. As semiconductor technology has developed, the number of components and the complexity of integrated circuits have drastically increased. Today's circuit designs require advanced computers and specialized software to help a designer complete a design without errors. The end product of the design process is the geometrical layout information, which controls where the transistors will be located and how they will be interconnected. These layouts are then fabricated on silicon by doping specific regions of the silicon surface through a series of repetitive steps, such as patterning, deposition, and etching. After the wafers have been fabricated, they move on to testing and packaging. In testing, the wafer slides beneath a probe card. Thin metal probes make contact with each pad on the circuitry, testing the flow of electrical current. A computer keeps track of which circuits have failed. In the inking machine, the failed circuits are marked with a black dot. Wafers are mounted on sticky mylar tape to keep them intact as the individual circuits are separated. an optical scanner aligns the wafer by checking specific points. Then, in soapy streams of water, a diamond saw cuts through the silicon wafer without cutting the tape beneath. The dies on the wafer are separated, but they remain attached to the tape. In die attach, a camera scans the individual die on the wafer. The electronic eye detects the ink blots that mark the failed chips and skips them. The good die are removed. Adhesive is placed in the cavities of a strip containing 4 lead frames. Each die is properly positioned and placed on the adhesive. A gentle scrubbing motion ensures a good contact. In an oven, the strips are exposed to high temperatures to cure or harden the adhesive. In wire bonding, thin gold wire is used to electrically connect the die to the lead frame. The thread bonds to the pads on the die and to the lead fingers of the frame. In slow motion, we see the thread connect to the pad and then to the tip of an individual lead. These pins or lead fingers of the frame are now attached to the microscopic circuitry of the integrated circuit. To protect the circuitry and its fragile wire bond, the devices will now be encapsulated in hard plastic. This requires a 2-sided mold. Between each operation, the bottom mold is brushed clean. The circular cavities will hold pellets of plastic molding material. When heated, the melted plastic will flow through the small channels to fill the rectangular cavities which will hold the devices. After several minutes, the encapsulation process is complete. The remaining plastic pellets and excess plastic are removed from the mold. The leads are now prepared for plating. Inside this machine, under high pressure, sand-like beads will blast away any remaining dust or specks from the molding compound and the leads. In ovens, the plastic molding is fully cured so it can withstand the plating process. In the plating process, the strips are loaded onto carriers and dipped in a series of chemical and water wash baths. In the plating baths, with anodes of tin and lead, the leads are plated with a layer of solder so that the chips can be easily attached to a printed circuit board. In this process, the individual devices are removed from the strips. The leads are cut from the frame on 4 sides and bent into their final configuration. The formed leads are then cut to their final length. The chips are punched out of their frames, and each one is now an individual package. The individual chips now undergo testing. They are loaded onto burn-in boards which will be placed in ovens. These boards consist of many electrical sockets. When connected, they allow electrical contact with each chip. In these boards, the chips will be stressed far beyond normal conditions. Weak chips are forced to fail prematurely before they are put into a customer's product. The loaded boards are slid into their electrical receptacles. In rows and rows of burn-in ovens, the chips are powered up and exposed to high temperatures for several hours. This stress encourages potential defects to occur faster. In another test, the chips are exposed to contrasting cold and hot temperatures before they are electrically tested. This large computer controls 2 testing handlers. Inside the handler, we see the chips move to the testing region. An electrical socket tests each lead to determine performance characteristics. Depending on the test results, the chips are sorted as those that meet specified requirements, those that meet lower requirements, and those that have failed. The chips that pass are marked with a logo. They are laser marked, visually inspected, and packaged for distribution. Soon, these chips will be placed on a printed circuit board. The maze of transmission lines are the conductive paths that signals use to travel between chips and to the outside world. In this cross-section of the circuit board, we see these transmission lines are routed through several different layers using channels called vias. The materials surrounding the transmission lines and the line's dimensions contribute to capacitance, resistance, and inductance, which affect the signal's performance. As with chip design, computer-aided design programs facilitate line geometry and routing, as well as the layout testing of printed circuit boards. These designs go on to be fabricated into the actual boards, which will hold various electronic parts. The bare printed circuit boards are loaded onto the assembly line. The boards are aligned by verifying known patterns with a video camera. In screen printing, solder in the form of paste presses onto the board through a brass stencil. Pick-and-place machines automatically inspect each electrical component before placing it where the solder paste was deposited. This is known as surface mount technology. Because of the various sizes and assembly requirements of the components, several different machines are used. Now the boards go through an infrared oven. The solder melts or reflows, binding the components to the top side of the board. Surface mount technology allows electronic components to be mounted on both sides of the board. This twin station temporarily glues tiny devices to the bottom of the board until they can be soldered later in the process. The circuit board is again subjected to infrared reflow to harden the glue and then flips back to the top side. The other way of placing parts on the board is the through-hole assembly process. Here, electronic components with wire leads are inserted through holes in the circuit board. The robot arm picks up multiple parts at one time. These parts are held in specially designed feeder mechanisms. Small components like these speaker connectors automatically present themselves to the robot arm for insertion. The wires that go through holes in the circuit boards are clinched from underneath to hold them in place until they are soldered. This eyelet setter, or rivet press, secures any large connectors located at the edge of the board which need extra strength. The circuit board now contains all of its components. An operator makes a final visual check. A wave solder machine does the final soldering. The bottom of the board is first coated with solder flux. This substance cleans the leads so the solder may adhere correctly. Bubbly solder preheats the boards before they encounter hot flowing solder. This secures all the leads and any components attached to the bottom of the board. It also fills any vias or other exposed holes in the circuit board. From beneath, we see the hot solder just touches the wire leads. The boards go on to be washed to remove contaminants and any remaining flux before they are electrically tested. Once they have passed their test, they move on to system assembly. The boards are placed in a computer casing. The speaker assembly and the data cables for the disk drive are then installed. The disk drive mounting bracket, along with the floppy drive, are inserted. The hard drive snaps into place and the drive power and data cables are attached. The power supply for the computer is installed, and the system is fired up to prepare it for the first phase of testing. Additional temporary memory and test cards are installed that allow software to exercise all areas of the system. An operator monitors the testing and verifies that the system is running correctly. The test cards are removed and the assembly of a personal computer is complete. What allows hardware like these machines to perform various useful operations is the flexibility of software. Software consists of many layers of programs. System software takes a computer task, which a programmer has written in a high-level language, and converts it using compiler and assembler programs into the binary machine instructions. Operating systems direct the flow of binary information through the components to control the mechanical operations of a computer. Application programs use the structure of the operating system to provide instructions which result in the wide variety of tasks performed by computers. These programs and the data they need are kept in the computer's memory when they are running. There are 4 basic elements to a computer. Input units feed information to the computer as electrical pulses, which are translated to the zeros and ones. Typical input units include keyboards, mice, and barcode readers. Output units provide the information requested of the computer. They include monitors and printers. In semiconductor memory, there are 2 principal types of circuits. Random access memory stores data that can be easily erased or updated. Known as volatile memory, the data is stored only as long as the current stays on.
Oh.
Come on, Mommy, I want to show you something.
Read-only memory, known as non-volatile memory, stores information even when the current is off. This memory contains permanent programmed instructions that enable the microprocessor to start. The processor, also known as the central processing unit, is considered the brain of the computer. Millions of program instructions are carried out in seconds, synchronized by a master clock. Inside of this computer, we find a microprocessor containing over 1 million transistors. The speed of a signal traveling through these transistors affects the computer's performance. In an ideal environment where there is no resistance, an electrical signal would travel at the speed of light. In a chip, however, resistance from the conductive paths between transistors and the capacitance of wires and transistors slows the signal speed. Most of the speed is lost, though, on the circuit board, where the signal faces an obstacle course of long transmission lines, inhibiting materials and the chip's packaging. As the signal travels from one chip to another, it encounters increased capacitance in the large surface areas of the pads, the solder, and the metal leg of the packaging. The most difficult are the thin wire bonds, which resist the flow of current. As circuit technology has evolved, we've seen an increase in the bits of data on which a chip or microprocessor can operate. This increased the computational power, but required more transistors and higher clock speeds. These increases have led to the high-speed chips used in today's powerful systems. With these fast chips, the delay on the board can cause an information bottleneck in high-performance computers. To overcome these problems, this high-end computer uses multi-chip technology to enhance performance. From the back, we see one example of a planar module with the outline of 16 multi-chip units, or MCUs, working together. Each one of these units contains the logic, formally mounted on several much larger printed circuit boards. High-powered chips are packed into these small units, along with a central clock chip that synchronizes with all the MCUs in the system. The board of the MCU is a high-density signal carrier substrate. It consists of 9 interconnected metal layers, insulated with polyimide coating and fabricated using semiconductor technology. The top layer is used to solder attach all the integrated circuits and connectors. This signal carrier, with its 3,000 to 4,000 solder bonding pads, has been cleaned and prepared for the attachment of high-powered chips. Non-conductive epoxy is dispensed in each of the die side cutouts. The epoxy is filled with microscopic diamond particles which conduct the heat away from the die, while the die remain electrically isolated from the substrate and from each other. Flux is then dispensed to the solder bonding pads of each die side area. When heat is applied during bonding, the flux removes surface oxides. This enhances reflow of the solder. In die bonding, this manufacturing facility uses 3 separate machines to accommodate the 3 sizes of fast chips used in the multi-chip units. The die are bonded to the high-density signal carriers using a chip-to-substrate interconnect called Tape Automated Bonding, or TAB. This TAB chip is densely packed with leads on all 4 of its sides. From the back, we see the inner leads fan out to the outer leads where the bonding will occur. Beneath the protective cover and through a microscope, we find the leads attached directly to gold bumps on the bonding pads. This technology eliminates the high inductance created by the thin wire bonds of traditional packaging. Once the chip is cut from its frame, it is carefully aligned for placement. Then, microscopic adjustments are made to ensure the leads line up with the die side bonding pads. A heating plate or thermode solders the extended leads. As the temperature increases, the leads are pushed down into the molten solder. The epoxy beneath the chips is solidified in a furnace, while a specially designed fixture applies pressure to each chip. In a robot work cell, flux is dispensed on the 2 PowerFlex bonding pads. The power consumed by the multi-chip unit is brought in through a power connector. The PowerFlex circuit, containing 4 copper conductive planes, is aligned with the large PowerFlex pads on the multi-chip unit. Thermode presses against the PowerFlex leads to bring them in contact with the pad. As the heat increases, the solder on the MCU pad reflows and the bond is complete. The process is repeated with the second connector on the opposite side. Flux is now dispensed on all 4 SignalFlex bonding pads. Each one of the 4 signal pads contains 269 etched lines or leads. SignalFlex connectors, consisting of 2 metal printed layers, transmit the signal between the high-density signal carrier and the planar module. Again, a thermode applies pressure and heat to bond the SignalFlex connector leads to the SignalFlex pad. Each one of these raised gold bumps connects to a signal lead on a chip. After washing and assembly, the raised gold bumps face upward. Near the clock chip, a unique serial number is encrypted by interconnecting special pads. Using this number, a computer, if necessary, can review the manufacturing history of the MCU without having to remove it. After extensive testing, a lid is placed on the MCU to protect it from mechanical damage. Finally, a pin fin is attached to the back side of the signal carrier. Much like our own bodies, the faster a chip runs, the more heat it releases. When these high-powered chips are operating, air is blown through the pins to dissipate the heat. These multi-chip units go on to be assembled into the planar modules used by this high-end computer. Producing computers requires many manufacturing industries and research from a wide variety of academic disciplines. Regardless of the type of computer or electronic product, they all require integrated circuits, which in turn rely on computers for their design and manufacture. Today, it takes computers to make computers. And, of course, a highly trained workforce to tell them how to do it and supervise the process.